So we're finally arriving at week number 8, where I'm going to talk about numerical methods. So I think it's, when we looked at the Lagrange multipliers, we started to arrive at things where they were getting just, you could still solve them in special cases. For instance, when we looked at the minimum variance portfolio, it was still possible to, we ended up with a linear system we needed to solve to do the Lagrange multipliers. Or to find the critical point for the Lagrange multiplier, the critical point for the Lagrangian. But pretty much anything beyond that, anything that's not sort of contrived to be simple, it's going to be far too difficult to solve. And so that's why we have something called numerical methods, which I sort of think of as just the logical extension of the guess and check method that I learned in elementary school. So you basically are just trying to make a guess. You'll measure how wrong you are, and that will hopefully suggest a way for you to improve your guess. And you want to do that in a way where you find the answer that you're looking for with the minimum amount of work. So the motivation for this, I'm going to look at a problem called implied volatility. And then I'll talk about two methods for solving that. So one is a bisection method, which is just a very easy approach to solving this implied volatility problem. Then Newton's method, which is not much more difficult, but theoretically it's a bit more, it has some nice theoretical results we can look at. Also, the nice thing about Newton's method is it can be extended for n-dimensional problems. And then finally, and I don't know if we'll have time to get to this today, we'll look at solving a problem with Lagrange method. So it's actually one of the same problems that I looked at in the Lagrange slides. But instead of just trying to do algebra once I need to find the critical point, I'll use Newton's method to try and find the critical point. So we get started by talking about implied volatility. So if we remember from the first half of the course, we were looking at the Black-Scholes formula for a while, mostly when we were looking at computing partial derivatives. And so this is just to remind you what it is, and hopefully I haven't made any typos in it. And if you look, well, I think I've got all of the, yeah. So the maturity, the maturity date of an option, this is a contract that I go and buy and sell in a market. And when it's written, it's going to have a maturity date. So it's good for 3 months or it's good for 6 months, something like that. It has something called a strike price, this is also something that's going to be written on the contract. So basically, once this contract comes into existence, the T and the K are fixed. So they're never going to change. And then there's a secondary market for these contracts. So once I have the contract, if it's between the time that it was written and the maturity, I can go to this secondary market and I can sell my option. So I don't actually have to wait for the conditions in the option to come to pass. I can go and find somebody else who is interested in having that same type of protection, and I can sell my option to him. And so if I sell the option, at the time that I sell the option, the price that I sell it for is going to be known because I give him the contract, he gives me some money. So I can look at the amount of money he gave me and I know exactly what the price of that option is. The option is based on some underlying asset that has a price S. And so I can also look in the market at the same time that I sold my option for this price C. I can look at the most recent trade for that underlying asset and see what the asset price is. So I can also assume that when these transactions take place, the C and the S are going to be known. And then I'm also going to assume that the risk-free rate is constant and that the dividend rate, so because options exist on kind of a short time scale most of the time, 3 months or 6 months, you generally know what the company's already announced when it's going to be paying dividends. So you know if you're going to get dividends during the life of the option or not. And the risk-free rate, well, it's definitely changing. It changes on a very slow time scale. So during the life of the option, you can assume that that's fixed. And so it turns out that if you look in this formula, so it depends on this D1 and D2 as well, you know everything except this variable sigma. So the only quantity that's not known is the volatility, and this is the one thing that it's actually quite difficult to know. That there's not any one thing in the market where you can just say, oh, this is definitely the rate of sigma. So going in the forward sense, when you want to use sigma as an input to this formula, it's something you have to actually estimate from data. So you have to look at it's trying to describe how wide the fluctuations are of this underlying asset price S. And so you can estimate it, but you can never actually know it. Whereas if you go to the market, on a particular day, I can see what was, when that asset changed hands, what were those prices, so I can actually observe S. The sigma, I'm not able to do that in any way. So the implied volatility problem, if I know every variable and the answer to the Black-Scholes pricing formula except sigma, then what I want to do is just sort of solve this equation backwards. So essentially, if I could, I'd like to isolate sigma and have a new function that's sigma as a function of everything else. But it turns out if we look at this guy, it's not exactly easy to do that. So extra credit if anybody can come up with a formula. And so what I want to do is, this is where I was getting at this trial and error thing. I want to just plug in values of sigma into my Black-Scholes formula, and I know what the call price should be, and for every different value of sigma that I plug in, I'm going to get some price, and eventually, if I just keep guessing long enough, I'm going to get a value of sigma that gets me very close to the price that I know it should be. So if I can get close to that market price C, then that's probably, that's the value of sigma that would have been in the market. And so even though I can't observe sigma, all the other things that I can observe imply a certain level for sigma. They imply a certain amount sigma. And so that's going to be called the implied volatility. So what I want to look at is if S, K, Q, R, T, and little t, so this is basically all of the inputs to the Black-Scholes pricing formula for a European call option, are known, and I also know what the price of that option is, then I can think of this as a function of sigma. So there's only one unknown in this highlighted side of the equation, and that's sigma. And the way I've set this up, I've put the theoretical price for a European call option minus the price for that option that I've observed in the market. So when I have the correct value of sigma, this whole thing, f of sigma, should be equal to 0. So finding the implied volatility really just boils down to solving this thing. It's called a nonlinear optimization problem. And I just want to find the value of sigma so that f of sigma is equal to 0. And this is something, like I said, you're not going to be able to just isolate sigma and have a nice f of sigma function that you can just plug in a 0 and find out what it should have been. So you have to solve this numerically. And so when I say solve numerically, there are lots of different prices, or lots of different ways I can try and do this. So the simplest one would just be to make a plot of f of sigma and see where it crosses the x-axis. And so where it crosses the x-axis is where f of sigma is going to be equal to 0, and that's what I'm trying to find. And then the value, so the x-axis in this case is going to be the sigma axis. The value of sigma, where it crosses the axis, is this f of sigma equals 0. And so to do that in R, the first thing I need is a function to compute the Black-Scholes call price. So this is just our implementation of what was on the slide a couple slides ago. So I've made an expression for D1 then the expression for D2, and then finally the expression for the Black-Scholes call price. And I don't know if you guys are getting used to looking at R yet, but basically what I'm doing here is I'm taking this expression, I'm assigning it to a piece of memory, a variable called D1. Then I'm taking this expression, assigning it to a piece of memory, a variable called D2. But then in R, if the last expression in a function, so because this has this keyword function here, this thing is a function, the last expression in a function gets returned. So when I evaluate this, I don't have to, you can if you want to say, assign this to, say, Black-Scholes call price, and then have one more line that says return Black-Scholes call price. Or you can just put an expression for the thing that you want your function to return as the last line. So that's why this is going to work. And then one of the nice features R has is it's treating every variable like a vector. So instead of having to do this in a for loop or evaluate the function by hand, 50 or 60 times to get a set of points to plot, I can just give a vector argument. So right now, I'm giving every argument is just a length 1 vector, and so I get a length 1 answer. On the other hand, suppose I take, so the second to last thing, this little s, so I guess I should also mention this is sort of bad programming, because none of the variables have very meaningful names. I just had to do that to make it fit on the slide. The first way I wrote this, only about the first half of it fit on the slide. I also think it's a lot easier to read if, when I say something like R minus Q, that should be R space minus space Q. You want to group things, so it's a little bit easier to see exactly what the function is. But in this particular case, I had another constraint which it needed to fit up here for the lecture, so I had to skip that. But if we look at the second to last argument, this lowercase s, this is where I'm putting in my value of sigma. And so when I call my function this time, instead of putting in a single value for sigma, I'm putting in 3 values for sigma. And what I end up getting out are 3 values for this Black-Scholes call price. So all of the other variables stay the same, but the first one here corresponds to sigma of 0.15. The second one here corresponds to sigma of 0.2, and the third one corresponds to sigma of 0.25. And now let's suppose that the option sold for $7, and I want to find sigma. So you can think of this as I want to find the sigma that's going to make my Black-Scholes call price equal to 7. But most nonlinear solvers are going to be set up just to solve this f of whatever equals 0. So you want to make a new objective function where the point you're looking for is 0. And I'm going to call that function f of sigma, and that's just going to be my Black-Scholes call price minus 7. And I'm going to plot that over a range of values of sigma and see where it crosses the x-axis. So the first thing I'll do is make my range of sigmas. So seq is a function that just makes a sequence. It starts at 0.05. It's going to end at 0.5. And it's going to go in steps of 0.01. Then fsig, I'm going to evaluate my Black-Scholes call price at all of the inputs that were fixed, and then at this entire vector of sigmas. So this is, I think this will end up being maybe 46 different values of sigma. So this is going to give me 46 different Black-Scholes call prices corresponding to each one of those input sigmas. And then I'm going to subtract 7 from that. And hopefully one of these will be pretty close to 0. And then I'm going to plot this. So I'll put sigma on the x-axis, and then this fsig that I've just calculated here on the y-axis. And then this optional argument, type equals L, is just going to plot it with a line rather than with points. And I get a plot that looks like this. And so on the left here, I'm below 0. On the right, I'm above 0. And it looks like at about sigma equals 0.25 is about where I hit 0. So that gives me an implied volatility. So I denoted that sigma sub implied. I think the book called it sigma sub imp of 0.25. And so this is a valid way of coming up with an implied volatility, but to do that, I had to evaluate the Black-Scholes formula 46 times. And if you look at this plot, I evaluated a whole lot over here where it really wasn't telling me very much, and I did the same thing over here. And still, the computed answer is not very precise. So I only plotted it in the steps of 0.01, and so it turned out that 0.25 was slightly less than 0. And when I put in 0.26, it was slightly more, but it was more slightly more, so that 0.25 was the closest one to 0. So that's why I picked this one. And so I was off by, so this is on the scale of dollars here, so I was off by about 1.5 cents. So it doesn't sound too bad, except that you might be trading, thousands or tens of thousands of these things, and so that ends up being a more worrisome amount to be off by. So what I'd really like to be able to do is compute this implied volatility to within a pre-specified tolerance. So right now, I've just sort of done these 46 things, and I've ended up finding out how close I was just by going back and checking my solution. What I would like to have is an algorithm that's going to keep going until, so for instance, if I was just going to buy one option, I would sort of want this to keep going until maybe the first significant digit was somewhere over here, and then I would be certain that I'm within less than a penny of the price that I'm aiming for. And so if I only wanted to buy one, well, if that's the smallest denomination of currency they'll allow me to use, then that will be good enough. So I want to get inside this pre-specified tolerance, and at the same time, to do that, I want to use the minimum number of function evaluations required. And so the methods, the general methods for solving this type of problem are called nonlinear solvers.